Okay, so now we are into the energy band diagram of a metal semiconductor ohmic contact, which is a special case of the metal semiconductor junction. Okay, so see here, we are going to take a metal and I'm going to join into a semiconductor. And the metal will have a Fermi level here. And the Fermi level of the semiconductor is going to be, they are going to be aligned in the same level. Since I'm going to take an N-type semiconductor, the Fermi level is close to the conduction band. Okay, the difference between the Fermi level and the conduction band energy is given by Q into phi s minus x. Okay, phi s is going to be the semiconductor barrier potential. X is going to be the electron affinity. When you see the Fermi level, when you see the in the metallic region, it is going to be Q into x minus phi m. Okay, phi m is the potential function or the work function for the metal, and x is going to be the electron affinity. So this ohmic contact is called as a metal semiconductor junction. A special type of a metal semiconductor junction is called as a ohmic contact. So if the barrier height, the Schottky barrier height is 0 or negative. So here you see the phi b. The phi b value is 0 or negative. Okay, so there is no barrier height between the layers. So if you want to know what is phi b, you can go to the previous diagrams. Here you see there is a phi b, right? The difference between the conduction band and the Fermi level is called as phi b. So that phi b you see, it is not here. It is 0 here. That phi b is going to be 0 or negative. It's going to be very, very minimum. So which means that the phi m and psi are very close to each other. The phi m, the metal work function phi m is either close or smaller than the electron affinity function of the semiconductor X. So since that barrier is going to be 0 or negative, they say that the work function for metal is going to be very, very close or smaller than the electron affinity value. For a p-type, it is going to be close or larger. So if you know for n-type, you can say for p-type, it's going to be exactly the opposite. So see the relation. When phi m is less than or equal to x, it is called as n-type. When phi m is greater than or equal to x plus Eg, it is going to be the p-type semiconductor. You know in p-type that Eg will come because your Fermi level is close to your valence band. So when you are computing any function, you have to come all the way down to your valence band and compute. So whenever you go for p-type, you will always have this Eg coming into picture, and whenever you go for n-type, you just take the electron affinity. So this is going to be energy band diagram. So when Qm is less than the electron affinity, which means that here we are taking the example of an n-type semiconductor. The electrons flow from the metal into the semiconductor, forming a positive surface charge in the metal. So in ohmic contact, it's going to be the reverse case. So electrons are going to flow from the metal into the semiconductor. Usually in a conventional metal semiconductor junction, the reverse happened. The electrons are going to flow from semiconductor into the metal. But here, because of having this special type of ohmic contact where we are adjusting the barrier height and all the work function, we are getting the reverse thing happening. You know, forward bias and reverse bias currents are going to be in different opposite directions, right? Same way. So whenever conventionally electrons will flow from semiconductor to your metal, but here the electrons are going to flow from the metal into the semiconductor junction, so thus forming a positive region near the metal. When more electrons are going to go away from the metallic region, that region becomes more and more positive. Okay, so this will set up an electric field across the junction. There is no barrier for the electrons in both directions. So the current is proportional to the applied voltage. A more practical method of providing this ohmic contact is to create a junction that consists of a thin barrier. See, the ohmic contact is not specifically designed for a metal semiconductor junction. It is just to take a metallic wire out of a semiconductor. Just I told you yesterday, right? When you have terminals and when you want to take the wire from outside to connect your terminals, for example, in BJT, you have emitter, source, and emitter, base, and collector. In MOSFET and JFET, you have source, drain, and gate, right? So everything is present inside the semiconductor. But how will we know where to connect? So if you want to connect to source or gate or drain, you need to take a wire from that region and bring it outside. So that is going to create a metal semiconductor junction. Those connections are going to be called as ohmic contacts. Okay, And these Ohmic contacts will have very very thin barrier. The potential barrier or the depletion layer is going to be very very thin. So they are also called as tunnel contacts. Such contacts have positive barrier at the junction and heavy doping in the semiconductor. Why positive barrier at the junction? Because the electron is flowing from metal to the semiconductor. So when such is the case, this metallic region becomes positive. The depletion region in the semiconductor becomes negative. That is what is given here. So you have a positive barrier at the junction and a heavy doping in the semiconductor. So this creates a very thin barrier separating the regions, so that through which the carriers can easily tunnel. So it shows the energy band diagram in a heavily doped ohmic contact, and you can see the VA characteristics are linear. So as you increase the voltage, the current is proportionately increasing with respect to the voltage, because the barrier is going to be very very thin, and because of very heavy doping, you will see a reduction in the barrier in the N plus region. So between the two metal and semiconductor, you are going to have an additional N plus region. This N plus region is very heavily doped. Because of this presence of very heavy doped N plus region between the metal and semiconductors, you have a drop in the energy band for all the levels, conduction band, Fermi level, and your valence level. So this is all about the ohmic contacts, what we are seeing. So ohmic contact is a special type of metal semiconductor junction. Any queries you have regarding ohmic contact, I am going to pause here for a few seconds.